Excuse me. All right, well, I am going to get started. With the next topic that we're going through. Again, chapter 5 and the initial parts of chapter 6, hopefully a review for you. So just getting back into taking antiderivatives and basic rules of that. And then last time we saw that the definite integral calculates the signed area, right? And so the big idea is that if I have a function that calculates the signed area, it's the definite integral, the signed area from, A to whatever. The fundamental theorem of calculus essentially says there's a connection between the signed area and the antiderivative, or an antiderivative. And this is the big thing, right? If I have a nice continuous function on a closed interval from A to B, then the signed area of lowercase f of x can be calculated by taking the antiderivative, plugging in B, and then subtracting, plugging in A into that antiderivative. These have to be the same antiderivatives, but that's the whole thing. So that's the fundamental theorem of calculus. If f is a nice continuous function, then I can find the signed area by use of the antiderivative. Right? That's the big takeaway. So that's a really, really big thing in calculus. That's why it's called the fundamental theorem. Anything that's called the fundamental theorem has to be a really big part of calculus, right? Fundamental theorem of calculus is going to be a really big part. We can find signed area. We can find area underneath the curve using antiderivatives. Okay. So let's do this one. Right here. We want to integrate from 0 to 3 the function 3x minus x squared with respect to x. So we want to calculate the definite integral. You could also say find the signed area under the function 3x minus x squared. Whatever you want to call that function, it's fine. And we'll use the fundamental theorem of calculus to do that. So the first thing we want to do is find the antiDerivative of this. We did antiderivatives last time. Now, lots of people have different notation when they go ahead and do this. When they find the antiderivative, and I'm going to find the antiderivative, and then I want to plug in 3 and 0, right? So the notation that the book uses, and I kind of like, is the brackets. So when I find the antiderivative, I get rid of the integral sign and I put the antiderivative in a bracket, square bracket. So taking the antiderivative means I raise the exponent by 1, divide by 2. That's our x to a power rule, as long as that power is not 1, -1, excuse me. And then minus 1/3 x to the third. So I put the antiderivative in brackets. So I know that that is the antiderivative. Now you could put a plus c there. But the fundamental theorem of calculus says this is going to work no matter which antiderivative you choose. So for convenience, most of the time we just say, well, let's let our constant be 0. Okay. And then we calculate it from 0 to 3. Notice that, again, it's very notationally heavy. The antiderivative symbol is on the left-hand side, and then the bounds are from 0 to 3. Or excuse me, the integration symbol, once I find the antiderivative, I put the bounds on the right-hand side. Okay, and that tells me this is prior to finding the antiderivative. This is post finding the antiderivative. So now I'm going to plug in 3. Into my antiderivative. That's what I get when I plug in 3. And then I have to subtract what I get when I plug in 0 into the antiderivative. Then I usually just turn to my calculator and calculate this. 3/2 times 3 squared minus 1/3 times 3 to the third. This gives me 4.5. This gives me 0. And so my final answer is 4.5. Yeah.
For exams and homework, does it matter whether you use fractions or decimals or anything like that?
Most of the time, homeworks are gonna ask you to round your decimals to 2 decimal places if needed.
Okay.
So most of the time, it's gonna say, if it's a numerical answer, write your answer rounded to 2 decimal places.
Okay.
Usually, if it's like finding an antiderivative, like if I'm just finding the antiderivative of 3x minus x squared, I want to keep it in fraction form. So, but it's like how to put things on the answer. But again, if it's a numerical answer, most of the time it's probably rounded to 2 decimal places. By the way, like I said, this is one particular antiderivative with constant 0. If somebody else would have used a different antiderivative, let's say we added a constant of 11 and did the same thing, what we're going to end up with, I won't go through all the details, but when I plug in a 3, I get 4.5 plus 11. And then when I plugged in zero, here I got 0. So what I'm gonna get is 0 plus 11. And so you can see no matter what constant you use, you're gonna end up at 4.5 as your final answer, right? So most of the time, when we're doing fundamental theorem of calculus stuff, we assume the constant is 0, just because it's less cumbersome than doing a plus 11, because you're gonna get 4.5 either way. And you can see no matter what you choose as your constant, that first thing, let's say I chose 14, 4.5 plus 14 there, subtract 14 over there, you're ending up with 4.5 again. So whether it was 11 or 14 or 168 or negative 672, it's all the same, right? You're gonna end up with 4.5, no matter which constant you choose. So that's why we don't have to tack on a plus C when you're dealing with definite integrals. Remember, indefinite integrals, you have to always tack on a plus C because you get the class of antiderivatives. Okay. I want you to try this one on your own. We're gonna integrate from 1 to 5 the function x squared plus 2 for these. Whatever you wanna. Do that. All right, so let's go through this. Oh, by the way, one thing I want to mention real quick, just as a typesetting thing, is something I'm sure you've seen before. But oftentimes the bounds on your definite integral are sort of inset and to the right of your integral. And then sometimes they're on top and bottom, like straight overhead, straight underhand, under the integration symbol, right? It means the same thing, whether it's straight over, straight under, or whether they are put inset and a little bit to the right. Okay, so it kind of depends on what computer program generates it out, you know, so, and the settings on that computer program. But anyway, so it just means the same thing. So let's take the antiderivative or take an antiderivative. An antiderivative of x squared plus 2 is 1/3 x to the third plus 2x. And then we're gonna plug in the upper and lower bound. Now, we always plug in the upper bound first. The one that's on top. And then subtract what we get by plugging in the lower bound. Now, at this step, I'll write the answer in fraction form, just so it's easier for me to write. This first piece is 51 2/3. This second piece is 2 1/3. When you simplify. When you subtract those two things, you get 49.33 or 49 1/3. Again, most of the time, it'll probably just ask you to round to 2 decimal places. Is that all right? Good. Now that we know kind of where this comes from, I do want to mention you can actually use your calculator to go from here to here if you have the TI-84 or TI-83 calculators. They have a way to do definite integrals. Now, the TI-84, TI-83 don't really have a way to do indefinite integrals, so you can't take an antiderivative. There's some calculators that have that capability. But for definite integrals, we can actually type that on our calculator. And so hopefully I can get this to project on the screen. There we go. So there was my calculations from earlier. Trying to get it so it's not. Clear this out. So if I want to do this integration here from 1 to 5, integrating function x squared plus 2. I go into the math menu that's over here on the left-hand side. And I go down to number 9. Now there's different operating systems your calculator can be employing. My operating system on my calculator right now is set for math print. And it's in the regular rectangular coordinate system. So when we go function integrate, my calculator generates out something that already looks like a definite integral. Okay. And so the lower bound was 1, the upper bound was 5, and then the function's expression that we're trying to integrate is x squared plus 2. Now, you have to be careful, you have to use the variable x and not the letter x. Does that make sense? There are like all these letters here. There's a T there, it's an O, P, Q, right, R. All the various letters. We want to avoid that, but we want to use the variable x, which is this key here. All right, so x squared plus 2, and then we want to make sure calculator knows that the variable we're integrating with respect to is x. And sure enough, you get 49.33. Now, if you hit that variable symbol and you got one of the other variables t or theta or n, that means you're either in parametric, polar mode. We want to be in function mode. If you've got a different variable. If you do not have the math print enabled on your calculator, when you go to math 9, it's going to look a lot different. It's not going to look like a standard integration. It looks like FNINT. And there's a specific order you have to plug in the things we just plugged in. The first thing you want to do is you want to plug in x squared plus 2. That's the function you're integrating. And then a comma. And then you have to say we're going to integrate that with respect to variable x. And then you hit a comma again. And then you hit the lower bound of 1. And then a comma again, the upper bound of 5. So that is the way and the order that you have to plug in if you don't have the nice math print. I kind of like the math print better. So if I ever show you stuff on my calculator, I usually use math print, but that's the order if you don't have it. Does that make sense? So all of this, once you've seen this, then that cuts out a lot of work about finding antiderivatives by hand, right? And plugging in numbers by hand. All right. What? So I want you to try this one. Just try typing it in. 6 minus x squared from 0 to 2. And then also I'll click on the next one, which is integrating sine of x. And I forget the bounds on that one, but I think it's 0 to pi. I'll flip the page. So 0 to 2, 6 minus x squared. With respect to x. And then, yeah, 0 to pi. Integrating sine of x with respect to x. All right, for this one, integrating from 0 to 2, 6 minus x squared. That's there we go. So 0 to 2, 6 minus x squared with respect to x gives you 9.33, roughly, or 9 1/3. Notice, again, that just goes really quickly once you've seen it. So once you've seen it once, Goes really, really quickly, hopefully. Anyways. And then if we were to do 0 to pi sine of x, the sine function is on our calculator already. Sure, you've seen that before, there's a sine function. Hit enter. And you get 2. So the area under the sine curve from 0 to pi is 2. Now, one thing about this second one, this second problem here, when we integrated from 0 to pi, when we are dealing with trig functions, and when you're dealing with trig functions in calculus, especially around the concepts of doing derivatives and antiderivatives, we need to make sure that we're all on the same page and using radians rather than degrees. Okay? Because that's one of the things about these trig function derivatives and antiderivatives, the ones that we know, saying, for instance, that the antiderivative of sine is negative cosine. That only works when we're using radians as our measurement. If we were using degrees, that would not be the correct antiderivative. Does that make sense? So there's something in the definition of derivatives and antiderivatives that the derivatives and antiderivatives that we all know and love work only with radians and don't work with degrees. And for the TI-84 calculator, you just make sure you're in radians by going to mode. And yeah, there it was. And make sure you're clicked on radians rather than degrees. So in calculus, we always use radians, and that's a definition of derivative thing. All right, and how that works out. Now, by the way, let's mute this one. Didn't have that. Thought I did. Let's talk about the fact that when we integrate from 0 to pi of sine of x, we get a nice whole number of 2. Okay? If you graphed the function sine of x, it's this curve with a wiggly line connected to radians. If we looked at that between the signed area between 0 and pi, it's that area there in blue. So if you scroll in, it's the area between the curve and the x-axis. That is not a nice geometrical figure, right? It's not a circle, it's not a triangle, it's not anything we have the. So it's kind of interesting that this area, which is connected to a lot of irrational numbers like pi and outcomes of sine of x, ends up as a nice whole number of 2, right? So we're saying that signed area in there's 2. And on the other case, it was 6 minus x squared. And that was from 1 to 5. Notice that I gotta do this the other way. From 1 to 5, 6 minus x squared. Did I get that right? Oh, that was from 0 to 2. I'm sorry. I did that. That should have been from 0 to 2. Sorry, I was thinking of the previous problem, which was 1 to 5, wasn't it? Shoot. 0 to 2. That's that area in here. Okay. That's that green area. So that was all positive. This area, again, connected to a quadratic. It's pretty interesting that you get a fairly nice rational number like 9 1/3. It is something to be said that if you would have gone from 1 to 5 on the integration of 6 minus x squared, you should have expected a negative number because part of that signed area is positive, but a bigger part of the signed area is a negative. And so it's perfectly okay to get a negative value when you use the fundamental theorem of calculus, because we can have negative signed areas, right? So it is okay to get a negative value out if that's what we're supposed to get. So if we go below the curve, we might get there. Okay. Let's just do one more of these. Let's do 1800 e to the 0.12 times x power. Integrated from 0 to 5. 1800 e to the power 0.12x integrated with respect to x. You can do this on your calculator as well. As long as you know where the E button is. All right, so the E to a power button is second, and then right here on the calculator, on this left-hand side. So it's second and then the natural log key. I've already typed it in, integrating from 0 to 5, 1800 e to the power. You can either write 0.12x or just 0.12x. But make sure it is 0.12 and not 12. And we get some fairly large number, 12,000 331.78. Again, most of the answers in this section, they'll just ask you to round it a couple of decimal places. All right. Well, that's really all I want to do as far as 5.4 goes. Obviously, there's lots of other examples that you could do. We can type calculator stuff in all day if we wanted to. But instead of doing that, let's start up in chapter 6 with substitution. Fundamental theorem of calculus says that the signed area is connected to the antiderivative in the way that we saw. So finding the antiderivative is really important. Most of chapter 6 is going to be different ways of finding antiderivatives. Okay. We obviously have some baseline rules that we learned in chapter 5, like how to integrate x to a power, how to integrate e to the x, so on and so forth, all our trig functions. But now we're going to look at more complicated functions and see how that works. And if you remember, the way we did integration, or I hope the way you did integration, was that you reversed the rules of taking a derivative. We were finding the antiderivative. We were reversing the derivative. Well, if you remember, there were more complicated derivative rules, like the chain rule of derivatives, and the product rule of derivatives, and the quotient rule of derivatives. What substitution does essentially is reverse the chain rule of derivatives. You guys remember the chain rule of derivatives? It says if I take a derivative of a function, inside of another function, then what I need to do is I need to take the outside function's derivative and then treat the inside function like a variable. And then multiply times the derivative of the inside function. An example of that would be taking a polynomial to the 7th power, like f of x equals the polynomial 3x squared minus 2x plus 5 raised to the 7th power. If I took a derivative of this, the inside function is this 3x squared minus 2x plus 5. That's the g in the derivative rule notation. So if I had something to the 7th power, if I had for instance, a u to the 7th power. And I want to take a derivative of that. I take 7 times u to the 6th power. And then multiply the derivative of the inside function. Okay. In my case, the u was 3x squared minus 2x plus 5. So I did it with u's here. You could also write the derivative with respect to x of f of some other letter. We'll call it u in this case. There's a reason I'm using u. Because when we do substitution, we'll do a u substitution. It's the derivative of f with the same input multiplied times the derivative of that inside function. So this is another way to write the chain rule. So f is equal to u to the 7th, f prime is equal to that. And RU in that example on the notes was simply, oh no, I forget it. Three x squared. I'm gonna look it up here real quick so I don't get the wrong one. Minus 2x plus 5. So if that's my function, I'll call it capital F. Then the derivative with respect to x is going to be bring the 7 out front. Lower the exponent by 1, and then multiply all of that times the derivative of this inside function, which is 6x minus 2. So that's taking the derivative. What substitution does is it starts with something like this. And we find the antiderivative. So we reverse this process. Okay. And when you reverse this process, what we're going to do is we're going to rely on substituting out an expression for some letter, which usually we call u. Right? That's why it's called substitution. So it's reversing the chain rule for derivatives. And we're going to utilize substituting out a u in order to do that. Does that make sense? Okay. Okay. So substitution reverses the chain rule, and it uses those u's to do that. Okay. In other words, if you look at the chain rule and then you kind of integrate both sides, you get the equation below, which is essentially the equation for u substitution. All right. So in substitution, the biggest thing we have to do is find what this u is, what this inside function is going to be. In lots of cases, it's gonna be easy to see because it's gonna be inside a more complicated scenario. Like it's gonna be the thing that's raised to the seventh power, or the thing that's raised to the sixth power. Okay? But the trick with that U substitution is that when we change over from using X's to U's, when I had the chain rule, I had this extra times U prime here. Okay? And so if we're gonna be integrating with respect to U instead of with respect to X, that's going to change. I can't just do a substitution out of a du with a dx every time. When I do the substitution out from a dx, I actually need to have the derivative of the inside function times dx equals du. I'll go through that and why it works, and I'll go through kind of an informal process. I won't go through the nitty-gritty details, but you'll see that. So I can't just simply start integrating with respect to u without changing out the differentials dx and du. All right? And it takes a little bit of finesse to do that. So let's do an example. Let's say I want to use substitution to find the class of antiderivatives, or just the antiderivative in general antiderivative of 100 times 4x minus 3 raised to the 6th power integrated. My integration is happening with respect to x. So integrate 100 4x minus 3 to the 6th power with respect to x. I think I'm gonna need some board space here, so this one. Now, in this case, it's pretty easy to see that the 4x minus 3 is the only function inside another operation, right? 4x minus 3 is a polynomial inside another operation of being raised to the 6th power. So I am going to set u equal to 4x minus 3. I tend to, and you don't have to, but I tend to write my substitution right under, and then I'll move over to the right when I start integrating and reversing. What I'm going to do now is I'm going to take the derivative of u with respect to x. Now, the derivative of u with respect to x can be written this way, right? Du over dx, delta u over delta x. I'm going to write it this way for just a second. That derivative, the derivative of this expression with respect to x, is 4. So I'm thinking of u as just like a function, like g of x or f of x or whatever. U equals this expression. So if I take the derivative of that expression with respect to x, I just get 4. So the derivative of u with respect to x is 4. What that means is that when I change out the differentials, if I want to change out the dx with a du, I have to use this type of substitution. I can't just swap out a du for a dx. When I swap out a du for a dx, I have to have du equaling 4 dx.
So would it only equal 3 because source to all one by the x?
Yes, yeah, because I'm just taking a derivative of this.
Okay.
So derivative of -3 is 0, derivative of the 4x is 4.
Okay.
So yeah, I'm just taking a derivative, standard derivative. By the way, it looks like we multiplied both sides by dx. And if you want to think of it that way, that's perfectly fine. There is a little behind the scenes manipulation about the differentials du dx and how that's related to the derivative that we're skipping, okay? So it looks like we just multiplied both sides by dx, and you can always treat it that way, but it is a little bit more complicated than just multiplying by dx. Does that make sense? So, okay. Now you can either do this substitution, or if you wanted to, you could have divided by 4 on both sides and use that substitution as well. So if I would divide both sides by 4, I could use that substitution. Either of these is legitimate, whichever one you prefer. Some people like doing this. Other people like doing this. And I don't particularly care. I'll show you on this example how both of them are going to end up giving you the same answer. So it's not big deal either way. Okay. Let's say I wanted to use this one. The du is equal to 4 dx. I have a dx over here. I need a 4 dx. What I could do is I could pull a factor of 4 from this coefficient and kind of put it with the dx. So if I was going to use this one, what I would do is I would take this 100 and say that 100 is actually 25 times 4. And since I'm multiplying everything, I can just pull the 4 backwards and kind of attach it with the dx. Right, put it right in front of the dx. And now I can do my substitute. Okay. The 4x minus 3 is going to get replaced by the u over here. And the 4 times dx gets replaced with this du. So what we get is 25 u to the sixth integrated with respect to u. That's an easy thing to integrate, because that's just it's like an x to the power function. Well, now we're just using the letter u instead of the letter x. So it's a u to the power. So what I would do is I'd raise the exponent by 1. Whoops. I'd get u to the 7th, divide by 7, and then do a plus c. And then I back substitute by back substituting, I mean, I change it back from u's into x's. Notice after I've integrated, there's no du dx to worry about. So the integration got rid of my du. And when I back substitute, the only substitution I have is a u substitution. So I just have to put the 4x minus 3 in for the u. And that's my final answer. Okay with that? Now, that's the way. Well, sometimes I do things that way. A lot of times I do things that way. I'll just use this one. Okay. You can also use this method. Sometimes I use this method too. Using that substitution what you would do is you would just say my integration this one has a dx already. So in place of the dx, I'm going to put a 1/4 du. And in place of this 4x minus 3, I'm going to put the u. So doing that gives you integrate 100 u to the 6th times 1/4 du. So that's our substitute. I probably should have wrote the word substitute there somewhere. And now because we have 100 times u to the 6th times 1/4 times du, that 1/4 and the 100 can multiply times each other. And you see, you get the same thing. That we had in this step from before. So we integrate with respect to u. And then we back substitute just in the exact same way we did over here to get our final answer. So whichever one of these versions of du dx substitutions you want, you can utilize. One of them kind of requires you to factor out a 4. The other one requires you to multiply by a 4. But they get you to the same spot, right? And in this case, at about the same point in time. Does that work? So that's the idea of substitution. We have a u, we take the derivative of u with respect to x, that gives us our du dx exchange. We exchange the u, or the expression for the u, and then we also do the dx du exchange, whichever way you want to do that. I usually do those at the same time so that we're dealing with all x's, and then in the next step, dealing with all u's. And then we integrate with respect to u, back substitute, and we have our answer. And obviously, when you get answers like this, it's perfectly okay, just leave it this way. You don't want to take 4x minus 3 and try to raise that to the 7th power on, by hand. That's not a very efficient use of your time. Okay. Okay, let's do another. We have 8x minus 20 multiplied times x squared minus 5x plus 18 raised to the 10th power. All integrated with respect to x. All right, so let's go through this. I'll go through this with you. The first thing we always want to establish is what the u is going to be, because that's the thing that sets up everything else. So we want to establish what's the inside function. In this case, we have 2 polynomials to choose from. But the one that's inside a bigger operation is the x squared minus 5x plus 18, because that's being raised to the 10th power, where this is just on its own. Does that make sense? So my u is going to be the x squared minus 5x plus 18. Now, before I start doing anything with the integral, first, I need to get my du dx exchange. So I take the derivative of x squared minus 5x plus 18, and I get 2x minus 5. So my du dx exchange is this, du has to be equal to 2x minus 5 times dx. Now, I'm just gonna use this one, okay? I'm not gonna manipulate it right now. We might get discouraged and say, well, is there a 2x minus 5 going around? There is, as long as I can factor out a 4 from here, right? So that's what I'm gonna do. I'm gonna rewrite this integration. I'm gonna factor out a 4. And then at the same time, hopefully this doesn't throw anybody off. When I factor out a 4, I'm gonna bring this back, the other piece, which is 2x minus 5, back in front of the dx, because I just like to see it next to each other. You don't have to do that, but that's what I tend to like to do. Okay. So if you left the 2x minus 5 in the front, that's perfectly okay. But just for visual nicety, I like to pull it to the end. Now I can do my substitution. So the 2x minus 5 dx, that gets exchanged for a du. The x squared minus 5x plus 18 gets exchanged for the u. The 4 stays there, so 4 times u to the 10th times du is what we're going to be integrating. Not really times du, but it's integrated with respect to u. And now I integrate with respect to u. Add 1 to the exponent, divide by the new exponent, tack on a plus c. And then I can back substitute. Four elevenths times x squared minus 5x plus 18 to the 11th power plus c. And that's the final answer. By the way, if you ever wanted to check that you got the right answer, you could simply take the derivative of this and see that you end up with this function here. Okay. And if you do take the derivative of this, you're going to have to apply the chain rule of derivatives to do that. So the 11 would come up front, you keep this the same, that change to a 10, and then you multiply by the derivative of the inside function, and then you'd end up with that. That function inside the integral. So if you wanted to check, you could check by doing a derivative, and by doing that derivative, you'd have to apply the chain rule. Oh, sorry, didn't pull that down. Let's do another. So the first couple of examples, the inside function was inside some, and being raised to a power. In this one, we have x times e to a power. And that power is fairly complicated. So x times e to the 4x squared plus 5. All of that is integrated with respect to x. Okay. What do you think the inside function on this one's gonna be?
4x squared plus 5.
Exactly, that exponent of 4x squared plus 5. So when we make the u is gonna be 4x squared plus 5. Look at that. Yeah, you gotta pull that up. Probably use, I don't know if I'll go that far down. Most of it. By the way, once you get used to this, sometimes people will skip this step where they write the du over dx because they know the du is going to be the derivative of this times dx. Right? So we got du is equal to 8x dx. Now, if you want to use this, you can use this. If you want to divide by 8x, you can divide by 8x. If you want to divide by 8, you can divide by 8. I think that's the way. Since I look at this problem, I see an x there and a dx that I can pair up really easily. And already have the x times dx. So what I'm going to do is I'm going to divide both sides by 8 and use this exchange. I'm going to say 1 du is equal to x times dx. All right. There's kind of an art to using the right one. And you can use any of them, but it's kind of an art to see which one is going to require the least amount of work. Does that make sense? And in this case, it's going to be really easy to just pull the x over and put it with the dx. So getting an x dx is kind of nice. I could have also said, well, the coefficient is 1, and so break that 1 into 8 times 1/8. And then I can use this one. But again, that's a little more work than I want it to be. So I'll use this one. Again, I just kind of like to see it where whatever I'm my exchange here, I like to see that visually. So I'm going to bring the x that's being multiplied by e to this power all the way over in front of the dx. And so x dx gets exchanged for a 1/8 du. When I substitute, and I end up with e. Now 4x squared plus 5 is going to be my u, right? So e to the u times 1/8 du. the 1/8 isn't gonna matter. I'll just bring that out front too. Bring that back out front. E to the U. And now I'll integrate. Integrating e to the u with respect to u, remember e to the power. E to a variable integrated with respect to that variable just gives you e to the variable. It's a very nice function. So I get 1/8 e to the u. The du has been eliminated through integration. And now I just have to add on a plus c. And then when I back substitute, I just have to exchange that u out for my 4x squared plus 5. So the final answer there is 1/8 e to the 4x squared plus 5 plus c. Now, before I move on, I do want to make just a note about writing in Moodle. When typing in something like this, so that's your answer. Make sure to use parentheses around the exponents. Oh. Because if you don't, then the exponent is gonna be 4x squared, and then you're gonna tack on a 5 at the end, right? So make sure you do that type of thing. Use parentheses around the exponent, so the entirety of the expression 4x squared plus 5 ends up in the exponent. Okay. And when you do type this in, Moodle will interpret what it thinks you mean the answer to be. So when you type something in Moodle, it will interpret what it thinks you mean the answer to be. So if you didn't write those parentheses and you see e to the 4x squared and then plus 5, you know something went wrong, right? So like you didn't have those parentheses. Another thing about Moodle. If you're gonna be typing, I'll make an easy one, x e to the x power. Let's say plus c, doesn't matter. If that was your answer, for instance. Now, that's not gonna be an answer in the substitution section, but in the integration by parts section, it will be. Stuff like this will be. Then what we have to do is use a multiplication between the x and the e. right? Because Moodle, if you type in XE, thinks the XE is a single word. All right? It looks at the commands, whatever it has, and it doesn't see that as X times E. If you write a number in front, it does see it as the number times E. So it recognizes that implied multiplication. But if you have two letters together, it doesn't recognize as that's one variable times another variable. It thinks you're introducing another third variable called XE. That makes sense. So X times E to the X power. Again, plus C. I don't technically need parentheses around this if there's only one term in my exponent, but. Is that right? So if you have a number in front, you don't have to worry about the multiplication symbol between the number and the E. But if you do have another variable in front, you get it. One of those weird things on Moodle. Okay. Any questions about that? Great. All right. Here's an interesting one. No, actually, let's skip that one. I'm sorry. So let's do this one. That last one doesn't work out very nicely, so I'm not gonna do that. Not yet. Here's another. So we have 12x squared divided by x to the third plus 16. That is being integrated with respect to x. So we've already done a polynomial raised to a power, right? Like x squared minus 5x plus 18 raised to the power. Our u was the polynomial inside being raised to a power. We've already done e to raise to an ugly exponent, and we use that ugly exponent as our u. Here we have a fraction with a polynomial on top and a polynomial on bottom. What's going to be my u?
The bottom of the fraction.
Exactly, the bottom of that fraction. The x to the third plus 16 is going to be my u. You can think of that in a few different ways. One of the ways you can think of that is that the bottom of a fraction is just, if I would have rewritten that, it would have been x to the third plus 16 raised to the -1 power. Right? So I could have rewritten it in a way similar to this using an exponent of -1 instead of like an exponent of 10. Another way you can think of this is in your head say, well, if I would have made u the numerator, the 12x squared, I would not have been able to pull anything out and attach it with the dx. Making u the denominator in this case allows me to factor out things and attach those to the dx. So whichever way you like thinking about y, we have to make x to the third plus 16 be our u, is fine with me, but that is the case in point. X to the third plus 16 has to be our u. And then when I take the derivative of u with respect to x, I end up with 3x squared. So my du dx exchange is that du is equal to 3x squared times dx. Again, it's kind of an art to see what you want to use. I want to use this as it sits here. Because what I can do, knowing the rules of how fractions work, I can factor 12x squared into 4 times 3x squared. And then I can take the 3x squared multiplied in the numerator, just like 3x squared multiplied on the outside of a fraction. So I can rewrite this as 4 over x to the third plus 16 times 3x squared dx. Everybody okay with that factor out of 3x squared? Now I'm ready to do substitution, or I'm ready to substitute. The 3x squared dx becomes a du. The x to the third plus 16 becomes the u. So that is an integration of 4 over u integrated with respect to u. We have to remember our base rules of integration. If I'm integrating 1 over u, that's natural log, right? So 4 over u, that's just simply going to be 4 times natural log. So I integrate, I get 4 times the natural log of u. Again, I will use parentheses when I write that on the board. Technically, we all should know that you can only plug in positive numbers in natural log. So some people would use absolute values around their u. And now I can back substitute. That'll give me 4 times the natural log of x to the third plus 16 plus c. Again, the nice thing in the back substitute is that after we've integrated, there's no more du. So this exchange in our back substitute is not gonna be a factor. Right, it's not gonna be a part of the back substitute. It's gonna be a part of the front substitute because I'm still dealing with integration. But after I've integrated, there's no more DUs and DXs to exchange. All right. And if you're typing this into Moodle, natural log is exactly what you think it should be. It's just ln. Right? So again, it recognizes two letters. That's why XE, it recognizes a single unit, is because when you get to things like this, ln is a single unit, right? It's the natural log. So, there we go. Here's another example of substitution. X times the square root of x squared minus 16. If you were gonna pick a u for this, what would you pick? The thing underneath the square root, right? X squared minus 16 is gonna be your u. That's inside another function, specifically the square root function. Now, this one's a little bit awkward. Not in the u du exchange, that's pretty straightforward. Du is equal to 2 times dx. Oh, excuse me, 2x times dx, excuse me. 2x times dx. Okay, I have an x I can pull out with the dx over there. I don't have a 2, so I'll probably just say, I'll probably use this one. 1/2 du is equal to x times dx. If I have it to factor out, typically leave it on the right-hand side, numerical value, to factor out. If I don't, a lot of times I'll just divide by 2. Like I said, I always like to rewrite square root of x squared minus 16 times x dx. The x dx will become 1/2 du. The square root of x squared minus 16 will become square root of u. Right this way. Square root of u times 1/2 du. Remember how to integrate a square root of a variable?
Raise power of half.
Exactly, yeah, you think of it, that's perfect. You think of square root of u and you rewrite it as U to the 1/2 power. Now, I'm also gonna just take this number out front. Okay. And then you use your normal power rule, x to a power or variable to a power. So remember, when I take the antiderivative, I raise the power by 1. 1/2 plus 1 is 3/2. And then I'm gonna take this coefficient and divide it by my new exponent. Sometimes people would rather say, instead of dividing by 3/2, multiply by the reciprocal. Sometimes that's easier. Dividing by 3/2, multiplying by the reciprocal, it's all the same. You end up with, all right, over here, 1/3 U to the 3/2 plus C. Now I back substitute. Black mark is killing me. And I'm bringing him too. We got 1/3 times x squared minus 16 to the 3/2 power plus C. Now, for purposes of Moodle, just leave it like that. Okay? For purposes of Moodle, it is perfectly fine to leave it that way. Okay. If you want to rewrite this, you could rewrite this with square roots in it. It's a little bit messy. The halves make square root of x squared minus 16, and then you have to raise that whole thing to the 3rd power, right? So to make it less messy in Moodle, you can just leave it that way. Is that all right? But it means same thing. Excuse me. Any questions about that? Now, there is one more example that I'll cover on substitution, but these examples give you a pretty good idea of what substitution allows you to do. Okay? And as soon as you set that inside function, it kind of determines how you're going to substitute. Again, there's different du dx exchanges that you can choose from. It's kind of an art to choose the one that's going to cause you the least amount of work. But whichever one you do choose, you'll end up eventually at the same place of integration with respect to U. Integrate with respect to U, and then back substitute. Any questions about substitution? I think you have all of the tools to complete that homework if you want. There is one more example that we're going to cover next class period in 6-1. And that's the last example on the notes. But I don't know if that's going to be a hindrance to 6-1 homework. Doesn't matter if it is. If you get one that you don't know how to do, it might be close to the last example. But other than that, you can do all of 5-1, 5-2, 5-4, 6-1 homework, right? In terms of what's due though, only 5-1 and 5-2 are due this Friday. Okay, only 5-1 and 5-2 are due this Friday. The 5-4, 6-1, you have the tools to do, but that won't be due till next Friday. Okay? All right, I'll see you next time.